All right, let's bring this home. So we just wrapped up determining a formula for the velocity of this diver who was 32 feet up in the air on a board, jumped up at a velocity rather of 16 feet per second, and then started coming back down. We worked out this formula for the diver's velocity, so we knew how fast they were moving at the time of impact with the water beneath them. Yes, there was water beneath them. That's sick. Um, Anyway, so there's a couple more questions I wanted to address related to this. So, and they both come related to this notion of at what point in time is the diver at maximum height, and then similarly, what is the maximum height that goes along with that t value. So I've got a bit of a visual demonstration here. So I've got this Pokeball, like a Lego Pokeball looking thing. You get the idea. And so I'm going to try my best to toss it straight up in the air so that it doesn't fly into my camera. So pay attention. A little high. Not quite so high. There we go. All right. So I'm proud of myself for not hitting myself in the face with it while I'm watching the toss. Anyway, so each time you saw the thing tossed, except for I think the first one that crested over the field of view of the camera, it goes up and then it comes down. So there's this instant in time at that point of maximum height when our Pokeball flies upward. Jolteon, I choose you. And then it starts coming back down. So there's this instant, where it's not moving. So at that point where maximum height occurs, what that ends up telling us is that there's this instant. Again, it's not a prolonged interval of time or anything. That tells us that our velocity is zero. We're not moving at that instant. In physics terms, there's an instant that the object is at rest before gravity begins pulling it back down. So since we have a formula for our velocity as a function of time, negative 32t plus 16, we can work that out. We can solve this guy for t, right? So subtract over the 16, divide the negative 32. So after half a second, I usually prefer 1/2. I just wrote it as 0.5 because we were doing decimal stuff. All right, so that's when our diver reaches max height. Now, what that max height is, this is often something that students will kind of end up tripping over. They'll get to this point and they say, aha, I've got my t value. And then to get max height, they're like, okay, well, let's take that and plug it back into something. And then they'll end up remembering, well, I think I mentioned this before, the last formula you saw. So they'll take this 0.5 and they plug it back in here. Hopefully you see why that's an issue, because setting this thing equal to 0 is how we got the 0.5 in the first place. So, you feed that in, you get a velocity of 0. Again, I've already said it. You said velocity, not height. So hopefully something, as you say, like a red flag goes off, but sometimes in the heat of the moment, people will just, merrily write down that the maximum height the diver reaches is 0 because they plugged that thing in there, or maybe they get some really tiny number because of round-off error. And, the diver's max height is 0.0002, feet, and it's that makes no sense. They started 32 feet in the air. So if you stop and think about it, you'll notice the issue. But yeah, we don't take this and plug it in here because that's velocity, like I said. If we want the max height, we need to take that value and plug it back into our position function. So instead of plugging it into v of t, we plug it back into s of t, the guy from the previous example. So we have negative 16 times 0.5 squared plus 16 times 0.5 plus 32. You pound out the arithmetic here in terms of what this ends up looking like, and we get 36 feet. So, yeah. Again, those of you who are metric, somewhere in the neighborhood of 12 meters. It's not exactly 12 meters, but you get the idea. All right, so that's most of the questions I want to deal with. There's one last topic that I want to address before we leave this section behind. So bear with me while I make some white space. All right, so the last thing I want to discuss in section 2.2 is kind of related to to something I've already foreshadowed, talking about the relationship between your car's odometer, speedometer, and accelerator. I haven't really talked about acceleration yet at this point. So hopefully, again, this is not completely brand new to you, but you can think of acceleration as how how your speed is ratcheting up or scaling down depending on if you're pressing the accelerator or the brake in the car, for instance. So we can think of acceleration. I'm going to abbreviate here. So it's a rate of change of velocity. It's how quickly velocity is picking up or slowing down, so to speak. So if acceleration is a rate of change for velocity, remember thinking back to that circle of calculus, we had rate of change down here in the corner. Rate of change is the same thing as tangent line slope, which was, right, that's the same thing as a derivative. So what that ends up telling us is if you wanted an acceleration function, you need to calculate the derivative of a velocity function. So v prime t, if you will. So, all right. So let's real quick take a look at this in the context of that example with the diver that we just talked about. So we had the v of t formula of negative 32t plus 16. All right. So if we wanted to find a of t, well, we need to calculate that derivative. So again, I'm going to fall back on that limit definition for how to calculate the derivative. So we feed t plus h into this guy. So negative 32 times t plus h plus 16 minus my v of t formula. I nearly said s of t. So v of t plus h minus v of t. Again, note the parentheses. They're important. Plus 16 minus a plus 16. Those guys are going to go poof. So, and you'll see negative 32t minus 32h when I distribute the negative 32 here. That should be typo time. So that should have said minus a negative 32t. I managed to leave that out, just pointing out my discrepancies. So if we're in a classroom setting, I do one of those that happens like at least twice a period. So anyway, so I understand why it's easy to overlook them yourself. But anyway, minus a negative 32t is going to be plus 32t. We still got the division by h, negative 32t plus 32t. Those guys are both gone. Now, we don't even need to do any fancy factoring here. If you get rid of them, all you have left is negative 32h over h, right? So it's actually just the constant function negative 32, which, if you look at the notes file, is like our British acceleration due to gravity in the units we use here in the States. So the units would look kind of like this: feet per second squared, technically, because you're measuring like units of velocity per unit of time. So it's feet per second, which we usually collapse down into negative 32 feet per second squared. All right. So that's what I wanted to talk about as far as the sort of these scientific lab type examples that'll end up generating this thing we call the derivative. So that's it for now. In our next section, we're going to start looking at what happens if we have other types of functions. So far, we've kind of focused exclusively on like power functions and polynomials and things like that. What if a trig function turns up, or an exponential, or a log? How do we deal with those things? So if you want to know, then watch the next one.